Welcome to Lecture B1, in which we will discuss the idea of interpolation. Roughly speaking, the idea of interpolation is as follows. We know the value of a function at isolated points, and we would like to estimate the value of that function at other points, in between those where we already know the value of the function. Well, one way that we can make this estimation is to make the assumption that the unknown function that we have, and after all, I'm calling it unknown because we only know it at isolated points. So in most places it is unknown. So what we can do is assume that this unknown function is a polynomial in between those points where we know its value. And so our goal then is to try to find a polynomial that will agree with the known values of the function at those places where we know it, and will hopefully be close to the correct value of that function at other points as well. And to illustrate this idea, let's look at an example. Now, I'm going to look at a couple of examples here, and you will notice if you look at the problems at the end of section 19.3, you will notice that the examples that I'm looking at are related, let's say, to problem 7 at the end of section 19.3. And this is important for you to notice because the problems that we will have at the end of this video and also the quiz problem will be similarly related to problem 7 at the end of this section 19.3. So let's see how this goes. Okay, so the first example, I'll call this EX1. Well, so this is example 1, and it says consider the linear polynomial that agrees with cosine x at x equals 0 and x equals pi over 2. If we use this to interpolate the value of cosine x at x equals 3 pi over 8, what value do we obtain and what is the error? So the idea here is that let's think about it for a moment. Let's suppose that we didn't know that this unknown function is cosine x. Okay? We don't know that. We don't know that it's cosine x. All we know is the value of the function at x equals 0 and x equals pi over 2. Now, we know, of course, that the cosine of 0 is 1. So here, this is the x-axis, and here's 0. So we know that at x equals 0, our function is equal to 1. And then we also know that cosine of pi over 2 is 0. So if we come out here to x equals pi over 2, we have this value. So we have only two values, and we're going to try to estimate the value of our own unknown function, which happens to be the cosine function. But we don't know that. Keep in mind, at this point, we don't know that it's cosine that we're looking at. We just know these 2 points, and we want to try to estimate the value of this function at x equals 3 pi over 8, which, of course, would be somewhere like this, 3 pi over 8. And so we're going to assume that this unknown function can be well approximated by a linear polynomial. And the reason it has to be linear here is that, think about it. So we can say something like y of x equals ax plus b. That's a linear polynomial. And we have two unknowns there, a and b, but we have two pieces of information. We know the value of the function at x equals 0, namely it's equal to 1 there. And we know the value of the function at x equals pi over 2, namely there it should be equal to 0. So we have two pieces of information. We have two unknowns, a and b, so we can solve for a and b and then find this will be our interpolating function right here. Once we find a and b, then we'll have our interpolating function, and then we can stick in x equals 3 pi over 8 to see what the interpolated value of the function cosine x will be at x equals 3 pi over 8. So let's see how this would go. Now, let me make a few remarks. You know that actually cosine function between 0 and pi over 2 is going to look something like this, but the linear interpolate is going to be just a straight line that will look something like that. And so the value that we're going to get is going to be somewhere like this, whereas the correct value for the cosine at that value of x would be up here. So it looks like there could be a significant amount of error, and that's part of what we're doing here, is to find out how much error there will be. Now, a moment ago I hinted that the way that we would find the interpolating function is by taking this expression here and making it give the correct values for the cosine at the 2 points that are given, at x equals 0 and x equals pi over 2. And I want to to be honest, that's not really the way we're going to do it. And the reason is that if we did things in that way, okay, for this case of a linear polynomial, that would require us to solve for two equations and two unknowns. And then when we went to a quadratic polynomial, it would require us to solve 3 equations and 3 unknowns. If we went to cubic, 4 equations and 4 unknowns. And you see the problem here. If we wanted a high-order polynomial, we would have to solve a very large system of equations. So we don't want to take that approach. We want to try to find a better way of finding the coefficients in the interpolating polynomial. But again, I'll just say one idea. Again, understand now, this is not what we want to do, but just to outline it for just a second, one idea. Okay, we would say y of 0 is equal to 1, because we know, keep in mind now, this is our interpolating polynomial. I'll go ahead and say polynomial here, just say poly. So our interpolating polynomial is y of x, and remember again that the interpolate that you use must agree with the function at the given points. So it must agree at x equals 0, and it must agree at x equals pi over 2. So we say y of 0 is equal to cosine of 0, which is 1, and y of pi over 2 must be equal to cosine of pi over 2, which is 0. Now, if we stick those two values into our expression for y of x, we would get y of 0 is equal to a times 0 plus b, and that's equal to 1, and y of pi over 2 is equal to a times pi over 2 plus b, and that must be 0. And this first equation, notice that a times 0, of course, is 0, and so we're just left with b equals 1. And then if we plug that into the second equation, we get a times pi over 2 plus 1 is equal to 0, and that would imply that a is equal to minus 2 over pi. And so now, in this simple case of two equations and two unknowns, we have been able to obtain the result rather quickly, and we get y of x is equal to minus 2 over pi x. I'm substituting in here this minus 2 over pi we found for A. I'm substituting it in there. And then for B, I'll substitute in 1. This would be the interpolating function that we would have. And let's just check it to make sure that it does agree at the endpoints. Is it true that at x equals 0 we get 1? Well, yes, because if we stick in x equals 0, this first term will drop out. And so we're left with just y of 0 is equal to 1, so that checks. And is it true that y of pi over 2 equals 0? Well, if we stick in pi over 2 for x, then we get minus 2 over pi times pi over 2, and that's minus 1 plus 1, so we do indeed get 0. So in this case, this approach for finding the unknown coefficients in the interpolating polynomial is fairly efficient. But again, I want to stress that if you went to a interpolating polynomial of high degree, this would require you to solve a large system of equations and a large number of unknowns, and this method is not the best method for finding these coefficients. So let me show you a better idea. Now, of course, we're going to end up at the same interpolating polynomial in the end. It will be written a little bit differently, but it will be equivalent, as we will see. So let's say better idea. And this may seem a little strange at first, but once you get the hang of it, I think that you will agree it's quite nice. So what we'll say is this. We'll say y of x is equal to x minus x1 over x0 minus x1 times f of x0 plus x minus x0 over x1 minus x0 times f of x1. Now, what does this mean? Well, notice that when we plug in to this expression right here, when we plug in x equals x0, the second term drops away because we would have x0 minus x0 on the top here. So this entire second term would go away. And we would, over here, we'd have x0 minus x1 over x0 minus x1. So we would just have a coefficient of 1. So when x is equal to x0, we get y of x0 is f of x0. So y agrees with f when x is equal to x0. And what about when x is equal to x1? Well, if we try x equals x1, notice x1 minus x1, this term will go away this time. And over here we have x1 minus x0 over x1 minus x0, so this is equal to 1. And therefore, when x is equal to x1, we get y of x1 is f of x1. So adapting or using a formula like this, we easily guarantee that our interpolating function y agrees with the unknown function at the points where the unknown function is known. And notice that we don't have to solve any system of equations. We already have everything we need here. We just need to plug in. So we get y of x is equal to x, and x1 here is the right-hand side, so x minus pi over 2. Let's see here. Just one moment. Okay, so as I said, we don't have to solve for the coefficients here. We just plug in the values that we have. So x1 is the x on the right hand side, and x0 is the x on the left hand side. And by the way, before I go any further now, what I'm doing now, this better idea, this is the one that you need to pay careful attention to for one of the problems that we'll have at the end of the video. So x minus x1 will be x minus pi over 2 over x0 is the left hand x, so that's 0. 0 minus pi over 2 times f of x0, so that's f. F is our f of x is equal to, let me just clean this up. F of x here is our function cosine of x. So we have cosine of 0, which is 1, plus x minus 0 over pi over 2 minus 0 times f of x1, and x1 is pi over 2, and cosine of pi over 2 is 0. And so if we now simplify this, we get x minus pi over 2 over minus pi over 2 and times 1. Well, we don't have to put the 1 down, of course, and this term all drops out because of the 0, and so we get minus 2 over pi x plus 1. Y of x equals minus 2 over pi x plus 1. And you can see, as we said before, this is exactly the same result that we obtained before. But I'd like to make a couple of comments. First of all, you could leave this expression in this form if you wished, rather than simplifying it down to here. I simplified it down to this point simply so that I could show you that in the end we get the same value that we had before. But, you know, if for instance, if our goal is, as it is in this case, if our goal is to find that interpolatory function and then to evaluate it at a certain point, well, this is a valid expression for the function, and in fact this is particularly valid here because it's nice and cleaned up, and it's also easy for us then to pick this other x, which will be 3 pi over 8, and see what our interpolated value is for that x. So I'll leave it to you to decide which form you want to use. I'm having some difficulties here. Okay, but now let's finish the problem. So whichever way you decide to get your interpolatory function or interpolating function, we see we're coming up with this same answer, and now the problem was to evaluate at 3 pi over 8 and compare the answer we get with the actual value of cosine of 3 pi over 8. So y of 3 pi over 8 will be minus 2 over pi times 3 pi over 8 plus 1, and the pi's cancel, and so we get minus 3/4 plus 1, which will be equal to 1/4. Now, if you plug into your calculator, you will find that the actual value for cosine of 3 pi over 8 is equal to 0.382. So the error here is equal to one-fourth minus 0.382, or negative 0.132. And that is a 34.5% error. So that is a fairly significant error that we have in using this linear interpolate. Now, I would imagine that all of you right away are thinking, well, if we had used more points originally rather than just 2, if we had used perhaps 3 points, then we could have gotten a better interpolatory function. And so that will be the next example. We'll say example 2. And let's see if I can just copy this. So now we take what we had in example 1, and we're going to make example 2. And this time, instead of a linear polynomial, we will look for a quadratic polynomial, and it will agree with cosine x not just at 2 points, but at 3 points. So we'll say at x equals 0, x equals pi over 4, and x equals pi over 2. And if we use this to interpolate the value of cosine x, we'll still look at x equals 3 pi over 8. What value do we obtain, and what is the error? So this time we're going to go directly to using the correct method. We're not going to talk about, the other way of doing it, where we might say ax squared plus bx plus c. We could indeed go about trying to approach a problem in that way, but we don't want to. Instead, we'll go directly to this kind of an approach. And so when you look at the problems at the end of this video or look at the quiz problem, this is the way you want to approach it. Now, since it's quadratic, we now want this kind of expression. Remember, a quadratic means it will be of degree 2 in x. But once again, we want this interpolating polynomial to agree with cosine x at all the points given. Now we'll call the 3 points given, we'll call this x0, x1, and x2. Just as previously we called it x0 and x1, now that we have 3 points, we'll call it x0, x1, and x2. And so the way that the formula will go in the quadratic case is this. we'll have x minus x1 times x minus x2 over x0 minus x1, x0 minus x2 times cosine of x0 plus, and notice before I even go any further, you can see how I've come up with this term, because this is the term that will make y of x0 equal to cosine of x0, because notice when I stick in x equals x0, we'll have x0 minus x1, which will cancel out with this x0 minus x1, x0 minus x2, which will cancel with this x0 minus x2. So when x is equal to x0, this term is just equal to 1, and we'll have y of x0 equals cosine of x0. And notice also that when we stick in x equals x1, this term goes away, and when x equals x2, this term goes away. So this is a good way to write the coefficient of the cosine of x0, and then in fact, I hope you'll maybe stop the video now and try to come up with the next coefficient, because it's a very similar idea. We'll have x minus x0 times x minus x2 over x1 minus x0 times x1 minus x2 times cosine of x1. And you see how that one will work. When x is equal to x1, we have x1 minus x0 canceling with this x1 minus x0, x1 minus x2 canceling with this x1 minus x2. So this coefficient is just equal to 1 here, and we get cosine of x1. But if x is equal to x1, this drops out, and we'll see also the last one will drop out as well. And then finally, we will have x minus x0 times x minus x1 over x2 minus x0 times x2 minus x1 times cosine of x2. And now if you look at this expression, I hope you'll agree, as we've already said, when x is equal to x0, you see this will be 0, so this term goes away. This will be 0, so this term goes away. And here we have x0 minus x1 canceling with this x0 minus x1, x0 minus x2 canceling with this x0 minus x2. So we just get y of x0 equals cosine of x0, which is exactly what we want. Remember, we want our interpolating function to agree with cosine x at x0, x1, and x2. And so this formula will guarantee that it agrees with cosine at x0. And likewise, you can check, and it also agrees at x equals x1 and at x equals x2. And again, notice that we don't have to solve any systems of equations in any number of unknowns. We just write these down and then evaluate. So this is a nice, straightforward way to go about finding these interpolating polynomials. And now let's go ahead and stick in everything. So we get y of x is equal to, oh, and by the way, now in problem 7 at the end of section 19.3, they're asking a similar question about sine of x rather than cosine of x. So you'll just make a very small change there. Okay. And so let's see. Let me take one quick break here. Okay, there's one thing I want to change about what we did in example 2. I took the error here to be the value of the interpolating function minus the value of the function that you're trying to interpolate. And as long as you're consistent, that would be fine, but your book uses that definition exactly the opposite. They take the value of the function you're trying to interpolate minus the value of the interpolating function. So let's just be consistent with what your book says. I'll just put an X through that and say 0.382, because that's the value of the function you're trying to approximate, minus the value of the interpolating function, and so we would get the error is positive 0.132 if we use that definition of the error. And we might as well, we want to be consistent with your book. That will certainly lead to the least amount of confusion. So let's just say error equals f of x minus y of x. Okay? And we will use that throughout. Okay, so now returning to example 2. We're going to go ahead and plug in these values we have. So x minus pi over 4 times x minus pi over 2 over 0 minus pi over 4 times 0 minus pi over 2 times the cosine of 0, which is 1, plus x minus 0 times x minus pi over 2 divided by pi over 4 minus 0 times pi over 4 minus pi over 2 times the cosine of x1, which is cosine of pi over 4, which is square root of 2 over 2. And then finally, for the last one, we'll have x minus 0 times x minus pi over 4 over pi over 2 minus 0 times pi over 2 minus pi over 4 times the cosine of pi over 2, which of course is 0. And so I think that I'll go ahead and simplify this expression just a little bit, but I don't want to do too much work on this. I'll just leave it in the following form. Remember again, cosine of pi over 2 is 0. Actually, we can go ahead, instead of writing cosine of pi over 2, we just go ahead and write 0 here. So we'll be left with, in the bottom of this first expression, we have minus pi over 4 times minus pi over 2. So the minus times minus will give us positive. We'll get pi squared over 8. And so we'll go ahead and write 8 over pi squared times x minus pi over 4 times x minus pi over 2. That's what this first term will simplify to. And then for the second term, we're going to get minus pi over 4 here and a positive pi over 4 here. So we get minus pi squared over 16. And when we take the, that's in the denominator, so we'll get minus 16 over pi squared times x minus pi over 2 times the square root of 2 over 2. And the third term, of course, will drop out because of this 0. Now, definitely, if we wish, we could go ahead and do a little more work to simplify this expression a bit more, but I don't think that that's necessary. Let's just leave it just as it is. So there is our interpolating function. And now let's find out what value that has at 3 pi over 8. And hopefully this is going to be a bit, and you can see that indeed this is a quadratic interpolating function here, because the degree, you see x times x, so this is degree 2 in x rather than degree 1. So we're hoping that this will be more accurate than the linear interpolating function that we obtained in example 1. And now we will see. So y of 3 pi over 8 will be equal to 8 over pi squared times 3 pi over 8 minus pi over 4 times 3 pi over 8 minus pi over 2 minus 16 over pi squared times 3 pi over 8 times 3 pi over 8 minus pi over 2 times the square root of 2 over 2. And let's see what this will give us. Y of 3 pi over 8. Okay, the pi's here and here will cancel with this pi squared. And likewise, the pi's over here, pi. This will cancel with that pi squared. And in this second term, we also see that we have 2 times 8. So the 2 times 8 in the bottom will cancel with the 16. And let's see then what's left over. We will have 8 times 3/8 minus 1/4 is the same thing as 3/8 minus 2/8. So we'll be left with 1/8 there. And 3/8 in the second term, 3/8 minus 1/2 is the same as 3/8 minus 4/8. So we have minus 1/8. And then we'll get minus 3. That's the 3 up here in this 3 pi. And inside we have 3/8 minus 1/2. So that's a minus 1/8. Minus 1/8. And then we have square root of 2. So we're left with minus 1/8 for the first term, plus 3 times the square root of 2 over 8. And now let's get our calculator and see what that gives us. Okay, so when I do this calculation, I am getting 0.405. So this means that y of 3 pi over 8 is equal to 0.405, and therefore the error, and remember now we're going to define the error to be, as we said right here, it's f of x minus y of x. So we'll get f of 3 pi over 8 minus y of 3 pi over 8. And of course we've already calculated f, remember, is cosine, and we've already calculated the cosine of 3 pi over 8 right here. It is 0.382. So we have 0.382 minus 0.405, and that will give us minus 0.023. And that is a minus 6% error. And remember that here above we had about a, what was it, I think, if I recall, a 40% error. So merely by going from the linear interpolating function to the quadratic interpolating function, we have indeed gotten a answer that, at least at the point 3 pi over 8, is much more accurate. And so that is the way that this will go. And so now let's look at some problems associated with this lecture. Okay, so the problems for this lecture B1 will be as follows. They're just like the problems that we just did, except that now we are trying to find an interpolating function for sine of x rather than cosine of x. So problem B1-1 says, consider the linear polynomial that agrees with sine x at x equals 0 and x equals pi over 2. If we use this to interpolate the value of sine x at x equals 3 pi over 8, what is the error? And you have these four choices here. A is minus 0.428, B is 0.174, C is 0.256, and D is minus 0.132. And for problem B12, consider the quadratic polynomial that agrees with sine x at x equals 0, x equals pi over 4, and x equals pi over 2. If we use this to interpolate the value of sine x at x equals 3 pi over 8, what is the error? And the choices here are A equals 0.1273, B is minus 0.0021, C is 0.0186, and D is minus 0.1857. And then finally, problem B13 will be given to you in class. So I strongly encourage you to go ahead and try to do these problems, B1-1 and B1-2, at home, and then there will be one more on the quiz in class. So that's it for lecture B1, and good luck.